I think we've been stuck for about 100 years now with two equally good, I would say, and equally tested almost fundamental theories. Quantum physics that applies to the small world and general relativity that applies to the large world. Wouldn't it be nice if you had a single particle? There are no twins now. So this is a single atomic clock, which by being in a superposition is its own twin. So already that's very bizarre. Einstein himself, incidentally, changed his mind multiple times about this. I mean, this is a signature of all creative people. It's sufficient to think of the brain as performing some kind of quantum computation. Quantum technology could be even more potent than drugs.
Welcome to a new episode of the Quantum Economy Podcast. Today I'm joined by Vlatko Vedral, one of the world's leading thinkers on quantum information and the nature of reality. Vlatko is a professor at the University of Oxford, and he has written several acclaimed books. His latest book is available today. It's titled Portals to a New Reality: 5 Pathways to the Future of Physics. In our conversation, Vlatko and I talk about the boundaries of reality, why Schrödinger may have seen further than we think, and how quantum theory might not only end up changing physics, but in the next few years, the foundation of what it means to be human. This is the Quantum Economy Podcast with Vlatko Vedral.
You said meeting on a Sunday is beautiful because we have some time to ponder some questions. And I've been looking forward to this because I've been talking to a lot of the CEOs of the quantum tech companies, but someone that really gets deep into the challenges of reality to an extent that I want to learn about is someone that I wanted to take on and to learn a lot about what you have coming on, because you have a new book coming out. And I wanted to ask you, are we at a crisis in terms of science, progress, physics, or are we at the emergence of a new, I would say, breakthrough of a new potential endeavor in understanding quantum physics or the foundations of reality? Where are we, Vlatko?
Yes, it's thank you for inviting me. It's a pleasure to be talking to you, Anders. And I think that's really the reason that prompted me to write this new book, Portals to a New Reality. So I think we've been stuck for about 100 years now with two equally good, I would say, and equally tested almost fundamental theories. Quantum physics that applies to the small world and general relativity that applies to the large world. And there have been virtually no experiments in the domain where both of these theories would matter. So that's one reason, as you said, that we seem to be stuck without any genuine breakthrough in the last 100 years. So I think partly, as I argued in my book, it's to do with the experimental advances. And quantum technologies have played a huge role here. So I think it's taken us a genuinely long time to be able to manipulate larger and larger objects in a fully quantum mechanical way. So I think now we are at that level, and that's why I thought it would be exciting to write about what we could be testing within the next 5 to 10 years. So that's certainly one reason. Another reason, and I think that's also of interest to you, is that I claim in the book that we haven't understood quantum mechanics in the right way. And if we do understand it as a universal theory of potentially everything in the universe, at least at present, then this would inform us which kind of experimental tests we should be undertaking. So I think it's a more consistent view. So it seems to me the reasons are really both technological as well as to do with our understanding of fundamental physics.
Yeah, 100%. And you want to shatter the complacency here, right? You say that basically the Newtonian physics is an attribute or is something that is on top of the foundations of quantum mechanics. And I think this is where you argue that we haven't gotten quantum mechanics in the right way.
You're right.
And you have been outspoken on the Copenhagen interpretation. You have nuances on how you tackle also the multi-world interpretation. And how these things are fundamentally, not understood to that extent that you want to propose. And giving a portal to a new reality. I mean, it opens the realms of, beyond the physical understanding, because your argument is obviously we are based on information. So everything is information theory. So I think you have 5 different approaches, pathways to the future of physics. Can we just, on a high level, just outline what are those 5 pathways?
Of course. So the key, and that's the first portal, really. So after introducing these 2 theories that I mentioned, general relativity, the theory of gravity, and quantum mechanics, I actually very quickly go into the first portal, which is this notion that people frequently emphasize the apparently, I would say, fundamental role of observers in quantum mechanics. And I think that's wrong to discriminate. There is a kind of dualism there, a bit like the Cartesian split between the mind and matter. And I'm advocating that actually there is no reason at all to suspect, at least at present. We don't know, obviously, and the future experiments may prove us wrong, which is exactly what I'm advocating we should be doing. But in fact, at present, we should simply treat any observer, be it another physical system, be it a living system, simple living system, even our own observation through our very sophisticated brain and apparatus, consciousness, self-awareness, all of that comes together. It seems to me, at least at present, that there isn't any reason to postulate that this is any different to other physical interactions that we encounter. And not only that, I think the statement is even stronger, that if you do suppose that our observation is the good old classical Newtonian observation, you're actually going to run out into all sorts of trouble and paradoxes. So my strong claim is that whenever you read about a so-called apparent paradox in quantum mechanics, it almost always comes from introducing this kind of Cartesian split, if you like, between the observers and the observed. Then the observers almost always obey the laws of Newtonian classical mechanics. And I think that's what gets us into trouble. So portal number 1 is really a test of what happens during a quantum measurement. And I gave an account in that chapter of how you can simply consistently analyze everything in the fully quantum framework. I think you already alluded to the fact that it is difficult because frequently we are even missing the right language. I think this is something that Heisenberg emphasized a great deal. He thought in the early days when he came up with his revolutionary paper exactly 100 years ago, he said that what's holding us back more frequently than not is the terminology, that we don't even have the right terminology. We keep using the classical terminology. And I think that's where we tend to make these kind of mistakes and come up with paradoxes that are not really paradoxical if you treat everything on an equal quantum mechanical footing. So that's the first portal.
Let me just pause you there, just we get to the second portal, because I just want to, before we get into a very complex coming back. So first of all, I 100% agree with you. This is also where I have a very, big challenge with some kind of mysticism and spirituality, views of the world. If we try to put them into words, into context and describe them, we take them out of the beyond, right? We take them into what we would refer to in philosophical of these sites and jenesites, the beyond, and that what does exist to physicalism. And we lack the words for that. But Do you leave room for the collapse of the wave function in your argument here, or do you see there is no collapse? Because when I listen to you now, it's kind of sort of sees that you leave the informational process, that everything that could happen, everything that has happened, and everything that can happen is a part of an informational processing. And when you talk about the observer, be it a device or an unconscious entity, do you even leave a room for the collapse here to manifest?
Only an effective one, which in physics there is this very funny phrase that we use, for all practical purposes. So what I mean by that phrase is that some observations in quantum mechanics, and the crux of the matter is really this question, whether any observation is really definitive and ultimate in that sense. The word a physicist would use is irreversible.
Right.
I've really detected, I've recorded something, and that's it. It's like that. And this event basically becomes a record even for the rest of the universe. So I think that such observations are only true in some kind of approximate limit. So quantum mechanics would say no, that's never the case. However, certain observations could be so complicated because information now diffuses through all sorts of channels that we don't even control. It spreads out into the environment, that you could call this a collapse of the wave function. But I think ultimately there isn't such a collapse. There is always a higher level of reality at which you can still analyze everything in terms of quantum information. So collapse, I would say, is there for all practical purposes simply because it's difficult in practice to undo certain kinds of observations. But quantum mechanics, on the other hand, is suggesting to us that that in principle these things could be reversible, and that's what opens up a very interesting reality. So you've got this kind of branching, as you mentioned already, some kind of multiverse picture, which I also argued against in the sense that it's still a classical limit that adds a little bit of quantum mechanics to it. I think that the way I would like to talk about it is that actually the whole universe is there as a single entity, but this single entity is fully quantum mechanical. Every aspect of this entity behaves like quantum information is telling us it ought to behave. So it's a very deep question. And that's, in fact, I think you hit the nail on the head exactly as far as the chapter is concerned, because what I'm showing is how you could have an apparent collapse, but within this fully quantum there's no contradiction between these two statements. That you make a measurement, it appears to you as though the result is definitive, the wave function has collapsed. However, at a higher level of reality, the universe is still fully quantum mechanical.
There are so many beautiful things to take on here. Can we write into that code? Are we the observers? Is there some kind of free will?
But it hasn't been tested at all. And that's my point, that somehow it seems to me that technology is going in that direction because we can handle larger and larger. Of course, the human brain may well end up being the last frontier. And these experiments are probably very far into the future. I don't think we can do that within the next 5 to 10 years. However, you may well be able to design experiments that involve artificial intelligence. They may well be quantum artificial. We could be talking about quantum computers with, let's say, million of quantum bits. And already there, the question of observation sounds like a very interesting one to me.
100%. And we can look at, if we, come beyond the error correction and move to error protected qubits, and we can scale that. That's a very interesting realm. So, but just one question before we move to the second pathway. So Sean Carroll, David Deutsch, who you've been working with also, both of them I think are very outspoken on the Everettian multi-world interpretation. But you precisely say it's Schrödinger that came up with the multi-world interpretation, right? But
yes,
yeah. On the multi-world interpretation, why isn't it complete? Why isn't that the pathway to?
Good question. I think that's almost a subtlety, and frequently what I think gets us into trouble is, again, this lack of the proper appropriate language that we should use. So I suspect, certainly I know when I speak with David that he fully agrees with what I'm saying. And I believe Sean Carroll agrees with this picture as well that I'm promoting. So I think what I'm advocating is that the many worlds picture, in which you have this kind of quantum superposition of these classical realities. Each branch is like a separate classical world, and then on top of it you put a superposition. In fact, it seems to me that this is a very special state. And in some limit, you can get that state within quantum mechanics. But the more likely than not, the states are far messier. You can't even define these classical realities within the fully quantum mechanical universe, which actually means that these realities are not even fully distinguishable. And the question arises then immediately, what does that even mean? What happens when we observe an entity of that kind? So I think these problems are all wide open. They have not really been tested.
No, I like that. That's beautiful. No, it's very interesting because, and also maybe you can just elaborate just for the audience why you say it wasn't Everett, it was Schrödinger.
Yes. This was a relatively recent discovery, possibly, if I'm not mistaken, in the late 90s. And it was the last lecture that Schrödinger delivered. I think in Dublin, we're talking about early 50s. I think 1952 is the year. And I think you can see even from the introduction, I think that paper becomes somehow, I'm not sure who digs up the paper. I think it's a historian of physics. And it so transpires that this appeared before Everett's many worlds interpretation. And it's simply Schrödinger's elaboration on his own, Schrödinger's cat experiment, in which he claimed that, quantum mechanics will never give you a resolution whether the cat is dead or alive, because everything just stays entangled and there is no collapse ever if you just look at the quantum mechanics at this global level. And interestingly enough, and I think there is an agreement even among historians of science that initially in 1935, Schrödinger really thought that this was paradoxical. But if you fast forward 20 years, slightly less, in 1952, he's now fully acknowledging that this is the most consistent picture of reality. And actually what he likes about it is that you never need to talk about any discontinuities in your equation. There are no sudden changes of anything. Everything evolves in a nice and a smooth way, as it does with classical waves. The big difference, of course, is that these are quantum waves. He was extremely negative about a concept that people call quantum jumps. He actually made very strong statements that, that if these quantum jumps turn out to be true, then I'd rather, had given up physics and did plumbing or something else. And in fact, you can see clearly in 1952, he ticks all of these boxes and says, if you accept this fully quantum mechanical view of the universe, we don't have any paradox, no discontinuities, no quantum jumps, no special place for observers either. So somehow it seems to me that he not only, some people may say he anticipates Everett, but actually I think he gives a more complete picture than Everett did. I think that is kind of the best as far as I'm concerned.
He just didn't brand it. It just could have labeled.
That's right. That's right. And that's another actually very important point, which is, and that goes back to the language aspect, that really it is important to name a new phenomenon that you come across, and how you name it is also crucial frequently, because if you misattribute a name, you will basically lead generations and generations of future physicists in the wrong direction potentially. Yeah,
It's the same with technology. I mean, artificial intelligence, first of all, is not artificial, and we don't know what intelligence is. I love it because it's my initials, AI.
Yes.
So
That's right.
but Kybernetics was probably a better description of it. But yeah, but I mean, we could ponder this for hours, but let's get into the second pathway. So we just walk through the book because I try to get the whole essence of your thinking.
So now the second one is going, so the first one was important precisely because I claimed that these foundational questions are unresolved.
Mm-hmm.
And if you think that certain foundational aspects will go one way, that will of course inform you what kind of experiments you think we should be doing. So somehow this kind of intuition as to what you think is the right way to think about a physical theory is extremely important. And even if we can't at present discriminate between some of these interpretations, there is nothing to say that in the future that won't be the case. And so I think this is extremely important. So what follows then is going into physics now. So, first I eliminate observers, and then I go in the direction of trying to probe this common ground between relativity, between first special relativity and then general relativity, gravity. And quantizing gravity, if you speak to almost any physicist, they will say that this is the biggest outstanding problem in physics. We have these two theories. They really are completely separate. Einstein's theory has never been contradicted experimentally in its own domain. We're talking about astrophysics, cosmology, really macroscopic objects, planetary galaxies, stars, and so on. And among these experiments, quantum mechanics really plays no role at all. So if there are quantum effects, and I'm advocating that there always are quantum effects, for all practical purposes, again, they are so small that you will never see anything in this macroscopic domain. So what I'm trying to probe now is, before we even get to gravity, which is my portal number 3, I'm saying there are lots of interesting things we can even ask about the nature of time. So time is a concept that has been discussed a great deal by physicists. Almost no two physicists even agree on what time is. In fact, even whether it's a fundamental concept that we need to treat in that way, or whether it's simply just an emergent property, or maybe even a fictitious entity we need to introduce because that's how we think, how we humans think in terms of space and time. So what
Just quick pause here. So when you say think, so basically I get like the mathematical aspect of time moves forward, but we could, based on physics or the foundations, we can move backwards, right? But when you say think, do you see think as a process from a human being, or do you see observe? So we observe quantum physical, would say, happenings, or some kind of settings in the universe, and we perceive them to time. Or do you see think, is that a process that is caused by a physical externalized entity? If you get where I'm going.
Wow, it's a good point. I'm not even sure I have an answer to that. I think there is certainly in two different ways. You can argue. One is that this is a fiction which our brain somehow finds easy to impose on reality, even though you could phrase all the laws of physics in a relative way, that you never need to talk about space and time. But when we calculate things, it certainly becomes a very convenient methodology to do it. So whether this is due to our genetic makeup, as you are suggesting, whether there is some kind of evolutionary advantage to thinking about it, is unclear. But the second point is very interesting, what you also raised, And it's to do with how would you think about the flow of time within this picture? So there could be something objective to that, rather than just an evolutionary accident that we find certain things easier. And the objectivity could come from this branching process in quantum measurement. That in a way, whenever you make even the basic binary quantum observation, you get these two realities that emerge out of it, which exist simultaneously. And you could actually think of the flow of time as the process of continuous branching of all of these realities. So again, going back to Schrödinger, it's probably not correct to think of it really as discrete jumps, but you should really think of some kind of continuous branching of all of these quantum waves that are continuously, if you like, interacting with one another. But it could well be that the physical origin to the arrow of time lies in this kind of continuous process of interaction and branching between these waves. So it's a very interesting question. Nothing in physics at present experimentally certainly tells us which way to go in this case. And that's actually partly why I wanted to have that chapter as a gentle... I could have, of course, put it together with general relativity, but I thought it stands really alone in its own right, because this question of what is time in the first place, and is there such a thing as irreversibility in time? Is the flow of time a subjective phenomenon? Is it really objectively like that in the physical world? Quantum mechanics, of course, adds extra interesting things to this, and we have never tested that.
Wow.
So the point I was making is that we have phenomenally good atomic clocks now. They're still they are fundamentally quantum mechanical, but what we haven't done yet is we've never put an atomic clock into a superposition of two different places. So this kind of superposition, which is the signature quantum effect, suggests to us that every quantum object can exist in many different places, many different locations, many different states at the same time. And what would be interesting, I thought, in that portal, is to probe what happens if you put a clock in a superposition and then take one of these branches, if you like, of the superposition on a journey. So this is Einstein's, the famous twin paradox, where one of the twins goes on a long journey, comes back and is suddenly younger than the twin brother. And of course, we've seen it in countless movies. You know, Interstellar maybe being one of the kind of grandest expositions of this phenomenon. So I thought, wouldn't it be nice if you had a single particle? There are no twins now. So this is a single atomic clock, which by being in a superposition is its own twin. So already that's very bizarre, but it's a direct consequence of quantum mechanics. And now, one of these branches you take on a journey and you bring it back. And when you bring it back, you've got this extremely counterintuitive state of affairs where you have one and only one clock, but it's in a superposition of two different times. It's younger and older simultaneous. So what does that even mean, right? So to me, I think the fact that we haven't tested this, we genuinely don't know what this could mean. First of all, we don't even know if it is like that. I'm advocating that I think quantum mechanics will pass this test, and relativity too, and I think it's going to go this way, that you will really have a superposition of this kind. And then to make the story even more interesting, to do with these multiple reference frames, multiple contexts of different observers, if you want to use that word again, the person who does this experiment lies outside of these two clock times, the younger and the older, and they have their own clock, which governs the whole experiment. In fact, that's yet another time which is different to the other. So you've got these multiple quantum states, if you like, embedded within these multiple times. And I think it's a really interesting picture of reality if it does end up indeed being like that. So that's exactly what I'm exploring. I'm exploring also the superpositions of processes that go in two different opposite directions. So that's exactly to test reversibility. Could you have a process that follows one arrow of time? So, you start with a hot coffee, and of course, with time, it cools down to reach the temperature of the environment. But actually, quantum mechanics again suggests that in principle, you could go backwards. There's nothing in the laws of physics. If you could control this coffee appropriately, there's nothing to stop you from going backwards. And so I'm now asking, what happens if you do this simultaneously? You have a superposition of two opposing arrows of time. Time goes forwards and backwards, and that sounds amazing as well.
I mean, from a mathematical standpoint, obviously, but you go beyond that. You suggest that, this could be actually applied, at least in theory, to macroscopic entities, right?
Yes.
And also very fascinating. I mean, we've thrown Copenhagen out of the window.
Yes. And, the simple, yes, that's a good point. In fact, because remember, whenever you mention an interpretation, there are so many different people who subscribe to each. And I think they're really usually different there. It's not even clear that there is one such umbrella that logically includes all of these views within one interpretation, like Copenhagen. But when I describe Copenhagen, I'm suggesting that they take this hybrid view of nature, and they really say that there is a macroscopic world which is fully classical. The information in this world is fully classical, obeys Boolean logic. And so to their view, it's extremely important to have this classical system inspect a genuine quantum system. It's a little bit how Niels Bohr, who obviously was the originator of the Copenhagen interpretation, thought about these things. And my point in this book is that this almost always, I think always actually, I don't even know of a single exception, leads you to a paradoxical situation. Simply because a classical system can never consistently couple to a quantum system. And you can see why Schrödinger exactly wanted to communicate this by introducing, more and more macroscopic entities into his experiment. So he said, think about a radioactive decay, which we all agree is quantum mechanical. There's no problem there. But now let me couple it to a bottle filled with poison, which is already a larger entity. And then let me put a living system inside this laboratory and ask, what happens now? Is the bottle broken or not broken? Is it at the same time broken and not broken? And then what happens to the living system? And again, these are very profound questions. And I think physics ought to be going, that's what I'm suggesting in the book, in this more and more macroscopic direction and really test some of these statements.
That's fascinating. I mean, it could have chose laugh gas instead of poison, but that's a different topic.
It would be better. It would be a more cheerful experiment. You're right.
Yeah. But anyhow, so that's wonderful. I mean, we could talk about time for hours. And then I very much like you started out talking about terminologies and how we describe things. And as a physicist and a genius thinker, you keep bouncing back to reality and the human being, the mensch, as I refer to, right? It's very difficult, but it's also at the same time fascinating. So many of the things that you have, from a quantum physical standpoint or from theory and mathematics taught about is philosophical ponderings that are very much aligned with how I see the world. So it's very fascinating to listen to you because you always have to come back to find something to hold on to, right?
Yes.
Call it reality or the human being or thinking or consciousness or whatever. So it's very, but I want to ponder that in a bit. So let's get to the third pathway.
Yes. The third one is then now applying this logic that in the previous portal was really only confined to the nature of time. And now it just asks, what about space-time? We frequently end up discussing different views of quantum mechanics much more than we end up discussing different views of general relativity. However, this is now becoming extremely important. What is the right way to think about general relativity even? Einstein himself, incidentally, changed his mind multiple times about this. I mean, this is a signature of all creative people. I think that they contradict themselves continuously as they go along, and they learn more and more about the subject matter. And of course, the experiments, in addition, then keep informing us about what's going on. So part of my confidence that the universe is fully quantum mechanical simply comes from the last 30 years of extremely, basically exponentially rapid development of quantum technologies. I think when I started, we could hardly manipulate, one photon, one particle of light, maybe one atom in a superposition. Then we started thinking about 2 photons, 2 atoms, and so on. It's still extremely microscopic. Round about 2000 onwards, people started to really do these things routinely with what we would call almost macroscopic systems, with electrical circuits, with superconductors, which are now possibly the most prominent platform to make quantum computers. So it all exploded, and I think it was clear, incidentally, as this year's Nobel Prize in Physics tells us, it is clear that we ought to be thinking quantum mechanical effects will survive in the macroscopic domain. So the chapter 3 now is looking at gravity exactly in this. How would we even test, even at the most basic level, before going into the topics that are usually discussed, like extremely strong gravity, black holes and things like that. And of course, our knowledge is probably much, much weaker there, almost complete absence of experimental evidence. But my question was, let's go in the opposite regime. Let's go into the regime of weak gravity, but let's add quantum mechanics to it and ask whether even at this lowest level of approximation of Einstein's theory, the weakest gravity you can imagine, is it true that gravity is still quantum mechanical? And we don't have an answer to that. This would be a hugely important experiment for physics, because it would settle once and for all the question of, should we even be quantizing gravity? There are many people in the community who suggest otherwise. They say, the two theories are not unified. However, and there are good reasons to think that they will never be unified, and maybe that we even shouldn't be unifying them. They just logically don't need to come together. And I'm arguing very strongly again, from my own bias, that the universe is fully quantum mechanical. I'm arguing logically that we should really include gravity. It would make sense somehow. This intuition at least would suggest to us that gravity ought to be quantum mechanical. So I'm suggesting an extremely simple experiment which involves 2 massive objects, each in a superposition of 2 different places. And now you allow gravity to couple these positions to one another. And what happens, this is a variant, incidentally, since we mentioned Schrödinger. I think all experiments, to put it a bit more strongly, all experiments in quantum mechanics are really variants of Schrödinger's cat experiment. So this is a Schrödinger's cat, but with 2 massive objects. And what happens if gravity is quantum mechanical is that these 2 objects become quantum entangled, exactly as Schrödinger had predicted with in his thought experiment. So to me, it seems that we are on the cusp of being able to do this technologically. We have 5 or 6 groups in the world now already attempting the first part of this experiment, to put one large enough object in a superposition of 2. So the difficulty here is really controlling larger objects in a fully quantum mechanical way. That's the main obstacle. Very similar, incidentally, from what's holding us back with our quantum computers, and the fact that we don't have a full large-scale universal quantum computer is simply because it's extremely difficult to control large systems with lots of degrees of freedom in a fully quantum mechanical way. So to make sure that none of this quantum information leaks out and basically collapses, as we said, for all practical purposes, where it becomes difficult to undo these things. So my suggestion is a very simple experiment. And like I said, it will only inform us. It's really designed to tell us whether we should even be quantizing gravity. If the experiment works the way that I think it would, it still doesn't tell us. This is the question I get very frequently. If you really demonstrate entanglement due to gravity, then how should we quantize gravity? And in fact, this experiment, because it works at a very low level of gravity, is not telling us much about it. It rules out certain approaches to gravity. However, many quantum versions of gravity would still be in the race, and I think that's the direction I'm then advocating. If this is confirmed, we should then be thinking about the next level experiment and so on.
So when I get you right, you're not trying to quantize gravity to that extent that from a conventional understanding, but you're trying to expand the understanding of quantum mechanics. We're trying to add it into the equation, so to speak.
That's it. Exactly to add it to the equations of gravity. And in fact, whenever you face this, that's why the question becomes extremely complicated ultimately. And I think the experiments I'm outlining are really the first step. I think they're not fully informing us as to exactly what we need to do. But whenever you are imposing quantum mechanics on anything, you need to decide which elements of this system you really need to treat quantum mechanically. Most of the time, you don't need to treat everything quantum mechanically. It suffices to treat only a few degrees of freedom, and you will be able to account for your experiment. So that's why I think this is not conclusive. You could be thinking about certain gravitational potentials that exist in Einstein's equations. And an educated guess, for instance, would tell us that they need to be now quantized. They need to be treated like quantum numbers. But in fact, we don't know. It could well happen that original philosophy of Einstein, the original one was that it's space-time and the bending of space-time that actually gives us gravity, in which case it seems to me that we would have to quantize this space-time. So both space and time would actually consist of small units, small chunks, just like light consists of photons. And this is one possible approach to quantizing gravity. But actually, we don't know.
Yeah, because it would eventually also then need that we need to find time as a fundamental force, and we're back to the argument.
Exactly.
Yeah. No, that's interesting. And yeah, there are so many things, but let's just go through the important pathways first, and the fourth one would be
on living systems. That's right. The fourth one is exactly asking this question of and it seems to me that this is the most likely future of research in quantum mechanics, that for a long time it's been confined to the atomic domain or simple molecular domain, because we know that quite a lot of chemistry at that simple level is basically just applying quantum mechanics to explain how atoms bond into molecules. But what I'm advocating in that chapter is that we should go beyond that, because if you really do think that quantum mechanics underpins most of chemistry, and as we know, living systems are really all utilizing chemical reactions in order to gain enough energy to stay far away from equilibrium, if you like this kind of Maxwell's demon metaphor.
I like that very much indeed, because there is so much emphasis on the equilibrium. And I talk about dynamic equilibrium. So it's not necessarily about staying away from equilibrium, but it's just striving towards equilibrium, but you're never in equilibrium. The homodynamism. The homeostasis is a static system, it's a dead system. So when you talk about life and the liveliness of life itself, the vitality, that's when you introduce the challenges in the quantum physical yes, and I think for the dream discovery, and I think a number of people have voiced this over the last maybe couple of decades even, would be that somehow quantum mechanics is crucial for the existence of life. So exactly in the dynamical way, as you said, not only trivially, it's crucial in terms of atomic structure, because we know that atoms couldn't exist
if the world was classical, and then they couldn't bond either into complex molecules if the world was only classical. So quantum mechanics is crucial for the structure. But actually the question is the dynamics that underpins all of this also quantum mechanical? And I think this is the portal number 4, where I'm advocating testing chemistry within living systems, but ultimately taking it all the way to the level of Schrödinger. Now, again, as I said, it's really difficult to believe that we'll be able to superpose, living and dead things. I mean, this sounds extremely hard even for the most optimistic quantum physicists. But what you can do is take a far simpler system like a bacterium, for instance, and even ask the question of, is a bacterium capable of being in a superposition of different states? If I try to couple two bacteria in the way that I was describing massive objects would be coupled through gravity, would they also be entangled? So are living systems fully capable of the full spectrum and range of quantum behavior? This has never been tested. So somehow, even though spiritually I think is going in the direction of Schrödinger, ultimately that's really what we would like to test.
Right.
Of course, that's not what we anticipate in the first instance. So I'm thinking really take the simplest system that we think we could control quantum mechanically and ask these kind of questions.
Yeah, and I would like to ponder that in biology, but let's take the fifth portal and then back to that, because I think there is so much to play with here also where Schrödinger came from. So let's work through the fifth portal and then return to that.
Yes, that makes sense. Fifth portal is trying to so I think again when we talk about physics at present, even as I talked about it now, we almost give the impression that that everything other than gravity is completely fine. So all other forces are quantum mechanical. We know how to account for them quantum mechanically, and that's the theory that we call the standard model. But actually, if you look at the standard model, it's more like a collection of almost frequently phenomenological and ad hoc rules and assumptions, and it doesn't really give you the feel that this is the final theory, even at that level. Even if you ignore gravity and you think that that's not really a big problem, the rest of it really is certainly an unfinished revolution. And so where I'm going there is to try to open that portal and say, let's not just focus on these other problems that we think are outstanding, but in fact, even our current understanding, the best understanding that most physicists would agree is there, is in fact unfinished. And there are many notions there that I think ought to be tested. So that's where I'm going. There are, for instance, the entities I talk about. So this all comes incidentally from trying to merge special relativity and quantum mechanics. And we end up having entities that we call ghosts. And it's a very interesting phenomenon because ghosts have to be there for quantum mechanics to simply comply with special relativity. Because in special relativity, all properties of physical systems have to have 4 distinct components. Very much like space, 3 components of space and 1 component of time. Einstein actually was saying that everything, every entity, take energy and momentum. There are 3 components of the momentum, 3 spatial components, and 1 component of energy. That also is a vector with 4 components. And so what's interesting in some of our theories is that while we have to acknowledge 4 components, frequently we cannot detect 2 out of these 4 components. That's what happens in electrodynamics. And as a result, they're called ghosts. So they're called ghosts because we need to postulate them to make the 2 theories compliant, but actually we then claim that they can never be measured. The effects can never be directly measured. And this obviously sounds a little bit weird. As soon as you learn about these things, and you look into
a
them a bit
a
more.
little bit weird. I mean,
Yeah, but
I took him to I'm a materialist, a physicalist,
yes.
one of the masters of quantum theory, and he's just telling me, "Hey, Anders, we in the science community, one of the smartest physicists that is around, working on wonderful things on expanding reality, we rely on ghosts."
Yes, it's not good. I agree. I was probably understating it a bit. I think it's yes. No, it's not a little bit. It's a disaster actually to have that. Yeah, you're right. Yeah,
It's beautiful.
you're right. And
Yeah.
and then to kind of soften this a little bit, which in my mind, in fact, makes it worse. And I'm advocating the opposite, by the way. To
Yeah.
soften this, people say, "Oh, these ghosts are not really quantum mechanical. They're classical. Yes, they need to exist, but we don't need to quantize them. Therefore, let's not worry about them." And that's even worse somehow. You're acknowledging a complete defeat, I think, here. So
Also,
I'm advocating.
classical ghosts that we are going to ignore.
Indeed, that's why. That's right. That we can ignore because the real ones are really fully quantum mechanical. Yeah. So
It's the foundation of absurdity.
yes, it's absurd. I
And
also think it's absurd.
we are physicists,
Yes,
and we
you're
are
right.
going to rely on classical ghosts that we
Yeah.
are going to ignore. And from
That's
there,
it.
we are going to build reality.
That's right. It's crazy, but we do need them because, of course, we acknowledge that this is the only way to make things comply with special relativity. And so, what I'm advocating is that actually, I'm advocating the exact opposite. I'm saying no. Let's treat them quantum mechanically, and let's really try our best to see whether they have effects. And so, I think they do. In fact, I've written a couple of papers that have been recently published, maybe within the last 2 or 3 years. And in fact, these are again, I thought these experiments would be perfect as the fifth portal because they are not just even going beyond what people consider the current best understanding, but they're even questioning what we call the current best understanding, and they're really suggesting that we should examine these concepts in more detail. So somehow it seems to me, and again, it's Schrödinger all over again.
Right.
It's always Schrödinger. It seems to me that if you really do quantize the ghosts, then under some circumstances, and these are very simple experiments that involve charges which are put in a superposition of different locations, very much like with gravity, but now we're talking about electrodynamics. It seems to me that these ghosts would actually be able to entangle to ordinary matter, exactly as you said, and that anyone who believes that that's the right way to think about reality must acknowledge then that they would also be real. They would be as real as the other two components, which of course we already know have effects. So I'm advocating that we test this because this is very important. The two, it's again not just a question of interpretation. At the moment, you can say it's a question of interpretation because we don't have an experiment to tell us which way to go. So even this ridiculously sounding picture that you have classical ghosts which you cannot see, but it doesn't matter because they are classical, there's nothing you can do about it because there's no evidence to the contrary. So I think these to me are extremely important experiments to pursue. And so actually, we may not just discover that we need to quantize gravity and actually how we might need to do that, but we may discover that we even need to revisit many problems in the standard model that we think are somehow done and dusted. But a whole new area opens up in this way.
It's fascinating. I mean, the whole scope that you open up, I think it's not only timely, but it's, as you said in the beginning, it opens the pathway to a new definition of our physical understanding of the universe. And
Yes.
Beautiful to tackle those various fields. But you always refer to back that it's always Schrödinger. And I was just to be curious, what do you hold of Schrödinger then? But he was, I would say he was an agnostic atheist. He wasn't, very religiously affiliated, as per my reading and understanding. But he was very inspired by Hinduism and Buddhism, as we see, and also when it comes to life. How do you see that, referring back to him and how we interpret Buddhism and Hinduism?
Yes, I think not just Schrödinger. I think he wrote beautifully, of course, about the Eastern mystical traditions. But I think most of that generation of physicists, even Heisenberg and Pauli and Bohr himself and many other people, I think
We
Jordan.
had the same in philosophy, by the way. There were many philosophers at that time that was very related to the Eastern philosophy.
That's true. It goes almost hand in hand in many ways. So I think what this suggests to me, again, as you say, science at its strictest, but of course no scientist thinks like that. All of us really do believe that there is an external reality, and we would really like to understand it better.
You're not allowed to think otherwise.
That's right. It almost sounds to me it's difficult if you don't have that assumption.
Right, exactly.
If you're a complete idealist, right? If you really think it's all in your head, then it's very difficult to motivate yourself to proceed to do anything with this. It seems to me what this signaled, by the way, at that time, is that reality is possibly not as materialistic. But again, one has to be very careful with this terminology, because probably materialistic, as according to, let's say, Newtonian, deterministic clockwork-like model of the universe. So I think somehow this shift towards information, that Schrödinger even used the kind of information like terminology even before Shannon or before this was fully developed mathematically. He called quantum states catalogs of information.
Yeah.
Literally every entry signifies a different experiment that you can do, and then you're attributing probabilities to all of these. And Heisenberg himself talked about properties of systems also as these tables of numbers. They also look like catalogs. They're all ultimately, by the way, catalogs of information. And that's what led in even to the uncertainty principle, that as you are multiplying different catalogs in different orders, you might get a different number. So if there is a catalog for the position and another one for the velocity, then the product of these two catalogs, it matters in which order you multiply them. You will get a different result. So basically, it seems to me that all of this suggested to the researchers at that time that clearly reality is not of the Newtonian materialistic kind. So that means that we should think of even the constituents of matter, atoms and, of course, subatomic particles ultimately. We should think of them more in this kind of probabilistic way, through these amplitudes that Schrödinger and Heisenberg used, rather than as definitively being out there in some concrete way. I think, it still is a materialistic picture. It's just you have to redefine what these objects ultimately. It clearly cannot be Newtonian materialism. That's been disproven. But certainly, it doesn't suggest to me that reality is not at all out there, that it's really all just a construct of our mind.
Well, why do you say that? Because, the perception, there is always, I want to ponder a little bit on consciousness, but how can we argue against that the only thing that is real is the perception of reality itself? So the subjectivity here is that we have some kind of, if you would look at, so my co-author, Dr. Florian Neukert, is an Austrian physicist.
Yes.
He has just recently been publishing a lot of what he called the quantum memory matrix. It's very much aligned with your work. And, and he's been working a lot of that experimentally. And basically here, we can basically read and write from a fundamental layer of universal information processing. And black holes can hold information, and there is some kind of compound, and there is a big crunch where you have some kind of singularity and can continue whatever. So everything that has happened, anything that happens, and anything that can happen is a part of that quantum memory matrix, right? But you could argue that the physical reality, although it feels real, and this is also a position that David Chalmers, the philosopher, also holds, that I share, is that when we have the goggles, when we perceive the virtual world, the perception of that world is real. So any perception we might have, it goes very much along with the simulation hypothesis of Nick Bostrom, and basically having a quantum computer that can simulate in reality. So why are you so sure that reality is real in the sense of a physical?
No, I agree. Not in that way. I think the way you put it, I think it's certainly difficult to argue against at the present time. And in fact, unless you can leave this system, closed system, if it really even is a simulation, as you are suggesting, it's difficult to tell this from within. In some sense, you probably would have to have some access to the programmer or something like that. So it's certainly physics certainly does not tell us anything of that kind.
I'll send it to you. We wrote about it, the God experiment, right?
Yes.
And the only conclusion we get, because I challenged 12 quantum physicists on this topic, I said, prove to me that we are not in a simulation.
Yes.
And the only thing that Flora and I came to a conclusion was basically when the entropy comes to a halt, there will be some kind of, if there's a simulation chain, if the foundational computer underlies the same physical laws, and there is no external programmer intervention, aka God, whatever, and every computer has the same simulation, eventually the computer would come to a halt, which could be basically a big crunch or a big bang, restart the universe. And this is kind of sort of, to me, without the math, saying that this is what Roger Penrose is talking about with the cosmological, circular infinity.
The cycles, that's right. There are these, exactly.
Yeah. So this is typically where we're heading, and therefore I was just very curious to your view on why are you holding on to the physical reality. I love it. I love the mensch, the human being, but it's hard to hold on to it.
It is certainly it's hard to refute in any way, and in fact even discriminate. I agree. I think for me it's more that I would like the same principles and the same stuff to explain all of the phenomena in the brain, which I think it doesn't imply. It's perfectly consistent with what you're saying. That's what I want to say, in the sense that clearly the brain has a specific way of inferring and modeling reality, and we are obviously constrained by whatever is happening inside the brain. But at the moment, I think I'm simply advocating that we have no reason to suppose that this is any different to what we are observing outside. Of course, we may well surprise ourselves at some level, but I think, again, to use the computational language, I think it's sufficient to think of the brain as performing some kind of quantum computation ultimately, and then obviously continuously also engaged in interaction with the environment.
Mm-hmm.
But I agree. How do you know that kind of interface doesn't affect you in a fundamental way? Actually, that it would lead you to conclude one thing is reality, whereas actually it's something completely different.
Yeah, no, I totally agree. I mean, there are many views on this. Obviously, we have panpsychism, we have Donald Hoffman arguing that, consciousness is fundamental and reality emerges. We have illusionism. But I would be curious, how much have you tapped into the brain in terms of, I know Stuart Hameroff, Roger Penrose talk about microtubules and quantum phenomena in the brain. From a quantum physical standpoint, wet, fluffy, and warm does not apply to the current.
That's right.
Many of the current. Yeah, but how do you see that? Do you think, because you kind of sort of hinted on that a couple of minutes ago, that the quantum, the brain could be some kind of quantum computer that we don't understand.
Yes, I think it's an important point, and I think you are right that there are kind of objections that are immediately raised against this view, and they are to do exactly again with controlling a large noisy system like the brain in a fully coherent way. So it's possible that, or certainly it's almost clear that at the whole level of the brain, if you include the size, if you include the relevant timescales for our thinking and so on, it's hard to imagine that itself is quantum mechanical. But I think if you go deeper into the constituents of various things, then almost invariably, as we know, somewhere down that line, just as we did in biology, you are bound to find quantum mechanics. In fact, being even fully, so if you make your distances small enough and your time scales short enough, then nature simply is fully quantum mechanical. There's nowhere else to go as far as physics is concerned. So what could be a model of the brain is that you've got this quantum phenomena confined to very small scales, but somehow all of these small quantum events add up ultimately to contribute to what we would call, let's say, macroscopic effects in the brain, like our thinking. So the fact that, let's say, it takes us half a second to do anything fundamental with our thoughts is not an argument against this also being quantum mechanical. So no one suggests that it's going to be fully quantum mechanical and it's going to be interfering over these timescales and so on. But what's not impossible, and I think in fact it must be the case, I can say it more strongly, is that it could be made up of lots of small quantum computations. They are probably very specialized. It's not a universal quantum computer, most likely. However, all of these small gadgets that could have evolved to contribute to our thinking may well be quantum mechanical. And this is completely unexplored, I should say. You mentioned Penrose and Hameroff. They've been actually promoting this model for a long time. I think it's been now 40 years, maybe even more. And we really still don't have any experiments that are telling us either way. So I think this is a huge. This would fit perfectly, the one of the portals that I was advocating on biology, but extrapolating it even further.
So, but so what you think then is basically at the foundational level in biology, so anything that is related to life and consciousness, because I talk about two fundamental things that seems atypical or different than a machine. One is the life itself, the vitality. In German we say Lebendigkeit, right? What does it mean like to? And the other one is the consciousness, basically the subjectivity, the agency, the sentience. How does it feel like to be something, the inner life of something, right? And so you would say that anything in a biological system to that extent would require quantum coherence at some level.
Yes, it is perfectly. Again, this is a big open question. Both of these transitions, if you like, the emergence of life from non-living systems, we don't really know how to explain this. Biology almost, of course, biology is actively exploring this domain, but I think we're confident with evolution only once we have a replicator that's complex enough and stable enough that the rest of evolution can really kick in and explain the emergence of higher level complexity. But I think what biologists take as primary in evolutionary biology is already ridiculously complicated for a physicist and a chemist. And the question, of course, for us is still, how does even this become a reality actually from the non-living stuff? And I think consciousness has a very similar flavor to it. Again, lots of us feel that it's not a switch. It's something where you probably have some kind of continuum. I mean, most of us acknowledge that certainly apes and mammals are conscious to a high degree, not the same as ourselves. But if you go down the evolutionary ladder, it's not even clear where exactly you would confidently switch off consciousness. So it's extremely interesting to understand. So it could be that quantum mechanics plays a role not only in the emergence of life, but as we now discuss, even in the emergence of conscious processes. None of this is understood. if there was an evolutionary pressure in that direction, it would then be very similar to the need for us to do quantum computers. So namely, nature would have discovered that presumably certain things could be done much more efficiently if you really do them fully quantum mechanically. So there could be an evolutionary pressure to evolve some small-scale quantum computation. However, it seems that most people would agree that at the level of the whole brain, it's difficult to imagine that the whole brain is in some kind of complex superposition of states. So let alone entanglements between two different brains and things like that you sometimes read about.
Yeah.
So this is, it seems to me, very unlikely. Unless there is some naturally evolved protected subspace in the brain which really has evolved to take care of quantum computation at that level. We really don't know.
Yeah, we got challenged by this when you wrote about the quantum information, quantum memory matrix, and basically people come out of the spiritual realm and relate to that is in terms of the Akashic records. I don't know if you're aware of that. That's basically the holistic part of tapping into some layer of consciousness. So when you said there is an internal process that you cannot connect or you cannot relate, this is very much, if you look at psychedelic experiences and the whole journey around Hoffman, and you see the whole essence of psychedelics in terms of ayahuasca and the spiritual realms of the Mayan culture and Guatemala and all of these. So here there seems to be like a tap into some higher state, and we argued against that, why it's not similar. So for lack of a better mathematical information processing explanation, they tap into the methodology, which we have done, over the past thousands of years, and new science have come up with a better explanation. But why would you argue that there could not be some kind of distributed consciousness in that information layer? So if everything is information, and we say at the foundational level that in the body or in the brain, Tonoli writes about an integrated information theory that gives life to or emergence of consciousness, pi. So there's a high pi, there's a high state of consciousness. So from that argument, we could say that we could also then give birth to a computational consciousness in a machine, right? But why wouldn't you be able to distribute that beyond a entity? So if you look at information communication today on a mechanical level, the argument would then be that a physical body could not distribute, whereas a mechanical body most certainly could. So if we look at consciousness as a emergent property of information processing, then why could we argue against a human being having a distributed consciousness way beyond the physical body?
Yeah, somehow to me it's again only the intuition that if it really gradually emerges through evolution, that it's somehow really localized in a sense that I have my own perception and my own feelings as you say, I get this sense of an objective reality, and I get the sense that what I see really is what the outside world is like, and even introspection, I get the sense that I understand the inner workings and so on and so forth. It seems to me that if you now want to take it beyond that, certainly not impossible, but it would require, if you want to preserve, let's say, some of these features that we have in quantum mechanics, it seems to me that it would require certainly a more sophisticated technology than we have currently.
Yes.
But nothing there rules out that at a higher level this could have been designed exactly as you were suggesting. So
Right.
it's very difficult to argue against that. I agree. I mean, it could be, but it's certainly not something we can do. I mean, just remember that we don't even understand. I think you raised this point about artificial intelligence, that it's not really. We don't really understand how human intelligence works. And most likely, even if you think it's a computation, it's certainly not the the paradigm that we use in our own computers, the kind of von Neumann architecture, centralized unit, and so on. The brain does something highly delocalized with
Yes.
much less energy. It's a phenomenal gadget if you think about it in
Yes.
terms of engineering. It's really a phenomenal gadget.
And energy efficient. It's not
That's
a good
it.
it's not
yes.
a good storage device, but it's highly energy efficient, and yes.
Incredible.
Yeah,
It's
so if you
incredible.
could tap that I've been arguing a lot about this, if you could have a storage device, so not having the stupid eyes, but you have glasses, you can capture everything, and you can start to have infrared and zoom and whatever, and you have a storage device where you can tap into that. How could you tap into memories and information in an externalized device that's much better at storage? If you download a thought or a memory, and you have more internalized memory, is there a difference in the perception? Would you even realize?
Yeah, I agree with you. Yeah,
and
so
that is also the same thing in terms of, like, if you have studies on mice or rats, if they're externalized controlled through neural impulses, if the neurons fire, and we know that from neurology, right? So the neurons fire, and then we perceive them onto the world. It's kind of sort of, we are not, serving the brain. We are merely projecting that onto what we call reality, because the firing happens even seconds before. So that it makes it just even more complex. The computer is processing, and then it arises into our conscious experience. Not like we think our thoughts, we think about our thoughts, but we don't know what lights the magic of the arising of a thought.
You're absolutely right. Yeah, I love. In fact, I love that direction. Right, that you can even detect these subconscious intentions and voltage increases before the person has even become aware that they would act in a certain way. So it's actually amazing that you can strap a person into electrodes and you can monitor them. And frequently, it seems that we are getting better at predicting more and more deterministically, more and more of the future of each of the people subject to these experiments. Incidentally, before I forget it, we're getting very close to the direction of how I conclude my book. The reason being that, of course, it's fun to think about these things. These are really the big questions that drive all of us. But even more so, I feel that whenever I talk about quantum mechanics, there's almost always a question from someone in the audience asking, what does this mean for us personally? It's okay, you described all of these experiments, we understand the significance for physics, but how does that change my own reality? And I try to speculate in a very similar way what you already mentioned in the very last section of the book, where I'm trying to channel Aldous Huxley, right? So Huxley, of course, the famous Doors of Perception. Of course, he advocated taking drugs, and that this would somehow loosen up the rigidity of our normal state of perception. And he felt that when you open the doors, everything becomes infinite, basically, rather than discrete, as we tend to think about things. So I thought it would be fantastic to think, and of course, this is pure speculation. I really have no idea which way this will go or could go. But I thought it would be nice to suggest that quantum technology could be even more potent than drugs. So what I end up advocating is that we are going to be soon faced, and I think people are already doing these kind of things, introducing an interface, a quantum chip that somehow couples directly to our brain. And it is possible. So this now, I think, is a direct consequence of the reality that I'm advocating in the book, that we really, the way we interface with the world is that we are forced into this kind of binary logic where something has either happened or not happened, a bit like Schrödinger's cat. We either see a living cat and we feel dead certain that the cat is alive, or we don't, and we feel equally confident about it. So I'm imagining this intermediate reality, which is actually most of quantum mechanics. And I'm thinking, could we somehow tweak this perception part, which we don't understand well. It would entail first understanding exactly how this image is created in our brain, but then really introducing a quantum component that would actually make us see potentially more of this reality that exists out there, the full quantum reality. So I end up speculating on this, but of course, again, we haven't even started performing these. To me, these are hugely interesting directions.
I take you on the next level of that. So if we then take that essence of what we call the quantum memory matrix, and everything in the universe is stores in informational events, right? Then we could think about free will as our ability to write into the universal memory, not just to read from it. So if you have that computational power, you could say that, it's not about just perceiving, but you could also write, because there's nothing that prohibits us to write into a information process. So you could write, so you could influence reality, right? So it is much, much more critical going down that pathway. And there are other things that are related. So we just recently also published, because I think externalizing artificial intelligence and creating an artificial general intelligence in a machine is kind of sort of handing over the authorities to that entity. So even if we would create a quantum computer that could give rise to sentience and a conscious entity, it would be so much more potent than a human being. So for us, it would be creating, God out of the machine, and we would be to ants to that super intelligence like ants are to us today. So what we argue is that the path forward is exactly what you're saying, is that, we have to tap into biology. You talked about chemistry. If we hack biology and chemistry and understand what Stephen Hawking referred to as our chemical scum, our body, we could basically understand it at a cellular level, and we could have to play with that. So romanticizing the human being or the mensch, I always say that let's not start with the AI, with the machine, but let's start with the human being, because we know there is something that we don't know that we refer to as human. And if we start that at the foundational level and build on top of that, then we have a higher likelihood to keep that conscious experience or that life phenomena. So I'm romanticizing the idea of an artificial human intelligence as in comparison to an artificial general intelligence, which I could think is to that technological realm that you are tapping into. And I totally agree. In the next 10 years, we will have huge breakthroughs in these understandings. And I am more worried about, the two of us having a conscious conversation.
Yes, I understand. I think that's correct. I understand how you feel, because it's so much easier. I think this is also simply an outcome of frequently least resistance, because it seems to me it's so much easier to improve what we currently have as AI and application, because we understand this. It's really, these are search engines that are just done to a greater and greater depth.
Yes.
However, it's completely, it seems to me, missing the point of it's certainly not simulating our intelligence, and I don't think it's getting us any closer to at all understanding how our intelligence works. And it seems to me that's what we should be probing as well. That's the scientifically interesting question. Whether, again, it comes from the integration between the two, it certainly is a possibility. And again, whether quantum mechanics is fundamental to that would be even more mind-blowing.
Yeah. No, and this is also the argument that I keep, like, can we fix one cell, right? Can we understand one cell? Yes, we can. So what prohibits us from understanding all cells? And the same goes for neurons, right? Can we figure out how one neuron fires, one region of the brain? What prohibits us from having 83 billion neurons and understand the complexity of how a strong computer? And the question is then, if we replicate that into a machine and we build a human brain, do we have a conscious experience, or is there some point where the lights stay on, but there's no one home to perceive them, right? You override something that we don't understand. And that's what I like to ponder on
Yes,
the whole.
these are beautiful questions, and again, probably as you can guess from what I've been advocating, I'm in favor of strong AI in the sense of that we will be able to artificially recreate that.
Yes.
It's difficult to tell with what technologies and what the extra bits are, but it seems to me the brain is certainly doing some kind of a computation. Again, it's fair to say we don't have the right model at present, but I don't think anything warrants going beyond this and saying, no, the brain is doing something supernatural. We will never be able to. I think we will be able to understand it the same way that we understand other things in science. It's just we may be really greatly surprised by what's required for this to really function in this way. So I think it's wide open.
Such a beautiful way to close out a wonderful conversation, I think, Vlatko. The book is called
Thank
Portals to a New Reality, 5 Pathways to the Future of Physics. Exciting stuff. I love it. I learned a lot.
Thank you.
Thank you so much for spending a Sunday afternoon with me.
Great pleasure, Anders. I'm really happy that you did this. Thank you.
Thank you so much.
Thanks a lot.